Pick of Destiny. Hackerboxes.com was generous enough to donate all of those. I think there's 22 of them, so those will be given out during the workshop. So thank you to Hackerboxes. One other sponsor that we haven't mentioned yet is MakerFabs. They actually do a bunch of power supply projects, meaning they do manufacture for projects. So they're integrated themselves, although they are about to be for a project. But they've done the CM work for a bunch of projects like the Light 3D printer, Caribou Light, Ionora, and a few others that are in the works currently. They are enticing folks to use their services with 2 $500 coupons. So if you have a cross-supply project and you go to MakerFabs, you get $500 off coupons. So consider it. They do great work, and we have a pretty long history with them, actually. So thank you, MakerFabs. Okay, EIM Tech is an ed tech firm. They actually have Jet, literally get in the car and drive Napa Valley. A colleague couldn't make it there, but they worked the demo area. You might have seen some of their ed tech kits. And a lot of people do ed tech kits. One of the things I like about theirs is they actually write books and document it extremely well. And that's, making an electronics kit is one thing, but actually getting it with a curriculum and support that anybody can pick up and start using is quite better. So they were a sponsor here. They had demos there. Check out their stuff. Thank you, EIM. A few schedule changes. You noticed that lunch or breakfast is not moving to 11, hopefully. If you didn't, it's not in the food lounge. Instead, similarly, lunch will be held in the same food lounge where we have the snacks and things like that. Yesterday, the Ubo Teardown and Hackathon was in 257, and due to the scheduling glitch, it looked like it was only there for half an hour. It was actually supposed to be like a 3-hour workshop. They get a whole room all day today, room 200. So if you're interested in joining that, really cool tech, and they have everything you need to tear it down and build applications on it. So check that out. That's all day starting at 11:30 today. And again, that room isn't being used for anything else, so you can go in and out as you'd like to see that. Okay, did I get all of that? Oh, some of you saw yesterday the talk by B-Sides organizers, which is a local InfoSec conference here. I embarrassingly have not been to that, but it would be very top of my list to go. Check it out. For those of you who are interested in local conferences, also there's later in a few weeks, 2 weeks from now, there is FOSSI, which is held by the Software Freedom Conservancy. I believe it's July 13th through 16th. And there's some flyers up on the registration desk for those of you interested in that. think that is almost it. Nandi?
Hello, everybody. Welcome to the last day. I have a few more mundane things to mention. One is that some of you have asked about a little bit more about study. I'll be sitting in the study lab in room 218 if you want to come by and check out what we have. I'm also going to walk back to the building through this lab so you can see we share a materials lab, wood shop, metal shop with the PSU art department. So it's much less today, but it's all block, so we can walk by and check it out. We'll be also doing Summer Institute July 18th through about August 10th, followed by Hack Days and a September show. So if any of you want to do a workshop or a demo or a talk, we'd love more people being involved, and then the lab will be open in the fall. And something else. Oh, we have a room, those of you who have to check out your hotel or whatever and have luggage, we have a room where we can lock your stuff up for the day so you don't have to lug it around. And also the door to the main building is not open today, but someone will be there to let you in. The coffee shop will be open until 3:30. Go, we have them open just for us. So keep it open. The one last thing is paperwork. I am a math professor in homework. So we gave each of you a post-it note to tell us we love ideas for the conference for the future and feedback. What did you know, speakers would like to see, types of events, workshops, we'd like to see a future teardown. And also we can look about this year. Sometimes we forget to keep track of that and we like accidentally drop it because we're trying to be innovative or something. Maybe there will be, I don't know, maybe Crowd Supply sends out a survey or some other thing. I personally like to tech, we'll put it up on a wall there, you'll take your post-it notes, but there'll be more to the desk. But it'll be interesting to see what comes out of it. We want to do these services participatory content, all of you help those that build the community. So I'd be very grateful for something. Yeah, just take your, and fill it out all day, it doesn't have to be right now. Take some more paper, fill it out. If you want us to contact you, you know, somebody else may not, but yeah, the goal is the idea. We're not trying to keep for ourselves the data, but like I said, we can create a special Google form for you if you want. But on that note, and come find any of us if you want to know more about study or Teardown or Crowd Supply or anything. We're around. Most people are wearing the red t-shirt on that. But yeah, you can find me by now. But thank you all for coming. This is it's not the conference that matters, it's sort of the community we build together, and the other great thing is very, very beautiful.
You can put the post-it notes on the wall next to the registration desk. We're gonna have a whiteboard, but just stick to the wall, we'll figure it out. Okay, let's get rolling. So next up is Christina Sear, who's going to teach us all about GNSS, which I think everyone is using maybe right now. So Christina, thank you for being here. Let's go figure out.
Thank you, Josh. Thank you, everyone, for coming here Sunday morning. I really appreciate it. I was talking to Josh. Josh was like, hey, we want to change the time of your talk from 3:30 on Saturday to Sunday morning. And I was like, will anybody be there? And you're all here. So thank you so much. I'm happy to be here, and I'm really excited to give this talk. So thank you for the opportunity. Whoops. Okay, surely there's present. Okay. Yeah, it didn't mess up. Okay, great. So we actually have a lot of audience participation in this talk today. So I know you didn't think you were coming to a workshop, but we're actually coming. You actually came to a workshop. We have light up balloons. We have the make your own GNSS take-home guide, and if we're able to get through everything, then we do have a song at the end. So. Okay, so my name is Christina Sear. I'm CEO of Detour and the Circle Phone, and here are my credentials. Just a little bit about the Circle phone, because everybody goes, why? And the Circle phone is basically an Android phone, but it has a round display. And I say just, but we had to do a lot of engineering, or I had to do a lot of engineering to make that work, both on the hardware side and the software side as well. The display drivers and all that kind of stuff. So it was solving the mobile phone monotony problem. You know, we've had the same rectangular phone since 2007, and it's just for people who want to try something different. There's actually a lot of science behind putting images in, cropping them into a round shape. Makes your Instagram look fantastic. It makes YouTube videos look amazing. Also, if you're reading text, it brings your focus to the center of the text, so it helps you absorb that really quickly. Most of our information that we absorb nowadays is pictorial based, and so this is a great medium for absorbing all the information that you have to take in. First question people ask is, what about my rectangular apps? What's going to happen with those? So we actually use a little known feature of the Android build, and that's freeform mode. So it's more like a desktop, so you can shrink and grow your application windows. You can even move them around your desktop to access the application icons behind. It's really cool. So I put a ton of it, because I'm an engineer and I couldn't stop. I put a ton of really cool things in it. So one of the cool things is that your selfie camera, normally on your phone, it's only 8 megapixels, but on this phone, it's 13 megapixels. So when I first designed it in 2018, that was a big deal. Of course, we have dual SIM because most of the Android users are outside of the United States, and they love price shopping for different SIMs, one for data, one for voice. So having the dual SIM was really important. We actually had a delay during COVID, imagine that, with our launch. And so while I was pretty bored during that time, so I added a temperature sensor so you could tell your temperature before somebody else tested it for COVID reasons. It's right next to the selfie camera. I added NFC because we hadn't had it up to that point. And back in 2018, we were still switching over to Type-C. And so there's actually a switch on the side. You can use either micro B or USB Type-C. But the only thing that people ever talk about is the dual audio jack. So in doing research for this phone, I talked to literally thousands of people about their mobile phone usage, both in person, actually mostly in person, and millennials in particular were expressing a sense of sadness, especially in 2019, that everybody was so heads down in their phone, they weren't connecting to the person next to them. And I thought, gosh, wouldn't it be cool to, hey, I can put a second audio jack onto it, and you can share your music and videos with the person sitting right next to you. And I thought that was really cool, and that's all anybody ever talks about. So, but it's also interesting to know that we're actually the most eco-friendly smartphone on the planet. Our enclosure is made of biodegradable materials. Like the Fairphone, we also included a screwdriver with the phone, so you can repair your own display. We send you an extra display, you know, because nobody has a lot of round displays. So, and you can change your battery, all those kinds of things. So it's user repairable. We started small. I put together, in 2014, I put together a ton of, these are not my phones, these are competitors, but I put together a ton of hobby phones to prepare to see if I could actually put together a smartphone. So I spent 2014, 2015 putting together a lot of hobby phones, and I couldn't buy the parts that I needed without becoming a corporation. So I became a corporation, and I slapped together like a 2G phone just to get feedback from people to see what they wanted. They started asking to buy the 2G phone, and I was like, wait, you want to wait for the 4G? But actually, that was really popular. So we did a Kickstarter. Susie? I said a bad word in this room. Sorry. We did a crowdfunding campaign, and it was it was successful. We delivered all the units in 60 days. So it was really a great way to start. I think that slide got moved. And then I searched for a round display, and I searched for a 4G module. And in 2016, they just really weren't available. But fortunately, I was able to test out a couple of different things, finally found what I needed. So in 2017, started making it, and then the module that I was going to use, the OEM got in a fight with Qualcomm, and I couldn't get the module for 2 years. It was really devastating to me, and it was really hard. So during that time, I taught other people how to build their own mobile phones at Maker Fairs, Geek Girl Con, and a bunch of other venues as well. So I've taught over 300 people to make their own smartphone, and I'm really proud of that. But of course, all I was dreaming of was being on the cover of Wired magazine. So this is an interesting picture because I was just so frustrated because I couldn't, I had developed the schematics, I didn't have the module, so I couldn't make the phone, and it was so frustrating. This is actually taken in my bathroom with a wooden model of the model that actually I was able to build the following year. So this is great. And then we showed off the original model that you saw in the previous picture at CES 2020 to over 1,000 people. We had our own booth. We were one of the most popular startup booths and got tons of people. It was kind of like when we had the 2G phone at Mobile World Congress, we couldn't even take bathroom breaks. There were so many people trying to see it. And we got a lot of great press coverage. This is actually the latest model. We got good coverage by CNET. Journalists from Japan really loved coming to see us. This is actually our second booth at CES. So of course the pandemic hit. So we were at 2020, pandemic hit, it was virtual, and then 2022, this is me. Oh, and the reason that I actually added this slide in, I love hair hacking. So this particular palette glows under black light, fluoresces under black light. So that's actually the only reason I added that slide. We were fortunate to be featured on the cover of Plastics Engineering last, 2 Aprils ago as the most eco-friendly smartphone on the planet because our plastic is made of biodegradable corn. And so that was really exciting. We even beat out the Fairphone, which I love them. They're also our competitor. So, and this year we received the award from CES. So this is really meaningful to me as a woman to get this award. It's hard for me not to break down about that. So thank you. Okay, so imagine that we have the dragon slide up again. So what you really came for was GNSS. And what's been happening in the last year is that, well, a couple things. In my personal life, we had a year-long delay in our dual SIM connector, and I was really bored. And this company came back to me. They had been asking for me to work for them 2 years. Let's see, they asked me in 2019, 2020, something like that. And so then they asked me again last year. And I wasn't excited about the project, but I was excited, well, the project was great. And the team was phenomenal, absolutely phenomenal. And they asked me to build some low-power GNSS solutions. So I built several, and they're some of the most low-powered that we have today. So I was really fortunate. I even got to do a chip-down solution. That was my first time to work with kind of HDI boards, and now I'm all about HDI. But after this talk, I'm just trying to give everybody a primer. So probably most of you know a lot about GNSS already, but some of you may not. So this is kind of the intro to catch everybody up to the same place. So I hope the number one thing, if you don't remember anything else from this talk, if you can walk away from this talk and start calling it GNSS instead of GPS, I'll love you. You'll have my fandom. Okay, so and then you also want to be able to name GNSS from 4 different countries. Understand how SBAS helps GNSS. Can everybody pronounce GNSS? You know, the G is silent. It goes and SBAS is SBAS, right? Okay, so it'll be in the song later. Just foreshadowing here. And then you want to learn and leverage various GNSS frequencies, both new and old. There's a lot that's come on in the last 2 years. You want to know about that, and you want to leverage that. And to create accurate and or low power tracking devices, depending on your use. So, these are the prizes. Can you get the balls out, please? Thank you. Okay, could please someone name one thing that you can track with GNSS? And you get a prize.
Battleship.
Cars, excellent. Battleship, excellent. Cows, children, excellent. Yep, okay. So, dirty little secret, a lot of companies came forth with child tracking devices about, 6 years ago? I think there were 3 more. Hey, raise your hand if you actually responded. You get actually a prize. So just keep your hand raised. This is actually my son, Cole Page. Can everybody give him a hand? Yeah. So, thank you. So dirty little secret, about 6 years ago, a bunch of companies came forward with child tracking devices. This is before you could do like find my phone, find my person, find my people, Life 360, all that kind of stuff. But retailers would not sell it for liability reasons, because if the child got lost and the tracking device did not work, it was a huge issue. So instead, they remarketed it as pet tracking devices. So if you want to get a really good kid tracking device, go ahead and just buy the pet tracking device, and that'll work pretty well. So yes, so not only do we track the things around us, but boats, planes, automobiles, and industrial machinery like tractors and things like that definitely use GNSS. That's why it's important. So how GNSS works. So, the name showed up before the dragon. Okay, so here's our dragon, and I named him Rover because in GNSS, the targeted device that you're trying to measure if GNSS is working on is typically called a rover. And so I really wanted to name him Henry, but we're gonna go with Grover today. Okay. And we're going to put the Dragon Tracker D-Track 100 on him. Includes maritime and aviation features. Up to 10-meter accuracy. It's a big dragon. It should be okay, right? So how GNSS works is that you have to have at least 4. So you would think 3 because, X, Y, Z, 3, but it turns out you need 4 satellite readings to be able to get a targeted location. And then basically you compare the time that the signal was sent, and the satellite information will give you that, to the time that it was received, and that's your clock, and then measure the distance. So I'm still learning how to pronounce these. But I just stick with ephemeris. So it's the data that comes off of the satellite. So that's the data that you want to store either on your device or send along. So the reasons that make this really important now, and you'll learn more about this later in the talk, are multi-frequencies and multi-GNSS. That's a huge mouthful. Don't worry about it. Just like, again, foreshadowing. L5 became available in 2021 for GPS. This is really important. Satellite-based augmentation systems, especially regional ones, highly improve GNSS accuracy. You should keep these in mind if you go outside of the United States with your tracking device, particularly outside of the United States. And a lot of GNSS modules have been released recently, not only to address the L5 band that came online in 2021, but also to address the newer satellite systems, and we'll get into those. So these are the 4 main global navigation satellite systems. See, that's what the acronym stands for. We even spelled it out here. So GPS, GLONASS, and this one's interesting too. There's lots of mispronunciations on the internet, and I'm probably going to mispronounce it here, but we're going to give it a try. So the way I remember it is hey, yo. So be, do. Let's all try it. Be, do. Be, do. So they're trying to switch to the BDS acronym, but because everything's kind of hard-coded in be, do. So let's see if they'll succeed. But hopefully we'll switch to BDS. But like I said, everything's still slow to change. And then Galileo is the one for the European satellites. Kind of late to the game due to political reasons. And they just went live in 2016. So there's also 2 more that you'll need to know about, and we'll go over those in the workshops. The Quasi-Zenith Satellite System, the QZSS, for the Japan. It's also the Asian Pacific region. It makes kind of the GPS and other signals more accurate. And then the Indian Regional Navigation Satellite System, IRNSS, and they're trying to change their acronym too to NAV-IC. So you'll see that listed as 2 different ones. So this is your personal GNSS guide in balloon format. Okay, let's hand out the balloons. Okay, so this is kind of a frivolous exercise, but if you go along with it in the fact that we really just wanted to try out these light up balloons, then you'll get the point of the exercise. So Joshua, are you here? Could you please hand out the LED portion? It's on the table. So please don't swallow the LED part when you're blowing up the balloons. Safety discussion here. I've actually not tried this yet. This is an unopened package of LEDs, but once I saw these, I couldn't resist. We have to do it. It's a dark room. How else are you going to see to write on the balloon except if it's lit up, right? You're all with me, right? Right. Okay, exactly. So, yes, please. Thank you. Okay, you have a black Sharpie. Please don't write on anything else but the balloon with the black Sharpie. Trust that you're all not 7 years old. But... Okay, so the trick with the balloon is that, yeah, I see people doing it already. So before you blow it up, go ahead and stretch it out a lot. It's easier to blow up if you stretch it. You know, if you've ever seen like a balloon design creator, they always like really stretch it. And then when you blow it up, before you tie it, don't blow it up all the way. You just want it to be round like a globe. You don't want it to be that teardrop balloon shape. Is that helpful? Okay, and I'm gonna try one along with everybody. May I have a balloon, sir, please? Thank you. Yes. Okay. Oh, that's a perfect example. I don't have to blow it up, okay? I'm just gonna borrow yours. Oh, and I'm so sorry. If anyone is allergic to latex, I have Mylar balloons for you. Oh, perfect. Thank you. Alvaro, you're the best. Okay, so this is about the size that you want. For two reasons. One, so it's more like a globe. You know, our globes are a little bit, you know, not a perfect round ball already. It's a little pointed at the poles. And when you ride on it, you don't want it to pop. So about this size is perfect. Nice. And in a perfect world, instead of clouds, there would have been satellites. So just imagine that those clouds are satellites and we'll all be okay. Okay, so in your perfect envision of the continents, just go ahead and draw the continents on there. And you only get 15 seconds. I know. But not everybody has balloons. So the people in front get a little bit longer time. So higher expectations for the people in front on your continental drawings. And we do have prizes for the most beautiful and, you know, quickest and first pop in the room. Yeah. Oh, you guys look so cool. Like, we need a shot of the crowd from this angle. I don't know how we can get it. Once we get all the balloons lit, maybe for the song, we can all like dance along with the balloons.
Request to speak louder.
Oh, thank you so much.
The volume's already up.
Oh, okay, thank you very much. Okay, and I've been requested to speak louder, and a lot of times, this has happened to me before. It's because I don't hold the microphone correctly or something, and get my voice in the side of the microphone. Okay, we almost have all the balloons all the way to the back. And I'm just checking the time here. We're actually ahead of schedule here. You all are doing really, really well. It looks so cool with all the glittering balls. Thank you everyone for playing along. I really appreciate it. Okay, so here's our assignment for your own GNSS reference balloon. So you have about 30 seconds to draw the continents. And then you want to draw the 4 GNSS. So it's really hard to say this name because it's like, is it plural? Is it not plural? Is it plural? Is it not plural? So it's the 4, and then it already has the word systems in it. So just draw the 4 GNSS. The first one is in the USA. The second one is GLONASS, that's in Russia. The third one is in Beidou in China. And the fourth one is in Galileo, and that's part of the song later. That's in Europe. And I did these little, they kind of look like butterflies. And actually satellites they just have wings that go straight out. But like if you want to put a satellite in each of the countries for extra credit, that's cool. Okay, and then we have the 2 regional GNSS. The QZSS, and I still call it IRNSS, or NAV-IC. And this is your first go-through. So we're doing the first go-through on the balloon, because I know the balloons will last about, 3 minutes after this talk. And then you'll go ahead and kind of repeat this process, but on the worksheet. So you'll have the a worksheet permanently. Did I just call it? I was trying not to call it a worksheet. It's your personal GNSS reference guide. Okay. While people are finishing up in the back, we're going to proceed on just a little bit in the slides. Did we run out? Another LED? Are we one LED short? Give them a ball, Cole. Give them a prize. And so sorry, I will make that right afterwards. Just give Cole your name. Oh, Joshua has a LED. Okay. Problem solved. Okay, while you all are working on that, I'm gonna drone on a little bit here. So GPS constellation arrangements, they're typically about 24 satellites. They always have about 27 so that they can bring the extra 3 online just in case something goes wrong. But typically they're in 24 satellite configurations. This is what the GPS constellation arrangement looks like. So the only thing that you get from this slide that I want you to remember from this slide is it's a constellation. It's an artificial constellation. Now I'm going to show you a whole bunch of slides. You only need to remember one term. Satellite generations. Can you say that with me? Satellite generations. So I went down a huge rabbit hole because I wanted to get a picture of every single satellite generation that was out there. And I kind of failed, but this is as far as I got, and I just wanted to share it with you. So the important part of this is that you want to keep in mind is that GPS 3F, these have special properties, and they've been coming on since 2021, and those are the ones that we want to start building around. They have new faculties, new advantages that we want to take advantage of. Okay, these are the satellite generations of Russia. Again, their newest generation has special properties as well. Beidou satellite generations. I couldn't find a lot of pictures of those. These, in this illustration, this happens to be incorrect. So these are actually, the illustration shows the GEO satellites, and those are not the Middle Earth satellites. They're the GEO, thank you, someone said it in back. And I'll say it later when the slide says it. But they're not the Middle Earth ones that we're concerned about. So I'll cover this more later, but the GNSS that we're talking about is in the Middle Earth orbits. Yeah, okay. The European ones. So it's really interesting. They never want to talk about, well, it's like they're a whole separate category. The GIOVE. I think if you say that out loud, what is that? GIOVE? Yeah. Excellent. Yes, that's exactly what it is. So A and B, the only reason that they were launched was to claim the frequencies. So they really kind of weren't operational. They were just like, okay, we're here. We're claiming the frequencies. So a lot of times when people summarize, they don't even include those, but I really wanted to see what they looked like. So in the pictures up in the corner here, you can see how they kind of differed from the ones in the bottom right that are available today. So, so these are the ones that are operational. So not all of these 12 have launched yet, but are in the process of being launched in the next couple of years. Again, they have like 24, they have a constellation of 24. So the interesting thing is, even though they were late to the party, they are more accurate, and you may want to leverage that when you develop your devices. So who run, like, I was like, wait, who's in charge of all this? You know, it's all these different countries, you know, how do they not run into each other? You know, like who does the coordination, all that kind of stuff. So I didn't know there's United Nations Office for Outer Space Affairs. Kind of sounds like Men in Black, you know, like association. But this is a subgroup of that. So if you ever see the acronym ICG, that's the International Committee on GNSS. And they keep track of the cooperation between everybody. Oh, your personal GNSS guide. Time for the paperwork. Thank you. Okay, this one I recommend not writing on with that Sharpie that I just gave you, because it'll go right through the paper. If you don't have writing implements, we do have a few extra here. Just raise your hand if you do need one. If not, you could tri-fold your GNSS guide, but it will go straight through the paper onto the activity on the back too, so you kind of just want to work lightly. So this is when we go into the regional, how the regionals are different than the main GNSS. And I really appreciate you all playing along. I heard Pat Dooley actually talked to me yesterday, and I said, yeah, I'm a little nervous. She said, no, but this is a warm and intelligent audience. And I was like, you're exactly right. That's exactly who we have here. Josh, thank you for helping hand out the sheets. I really appreciate it. Okay, so I'm going to go ahead and jump ahead. You all can catch up. So we're going to go over, you're going to fill in the same things that you filled in the balloon, so the 4 different systems. You fill in GPS, fill in GLONASS, Beidou, and Galileo. Okay, and then let me talk about while you're filling these in, let me talk about the regional systems. So the regional systems are actually not in middle Earth orbit, they're actually higher up. And because of that, they travel along the equator and they're able to do kind of an elliptical orbit. So it's kind of built on, I was trying to read more about this, but it's kind of built on 3 satellites. And somebody was raising their hand in the back, but Cole's getting it. They're getting a paper. So there's 3 satellites. How can I do this without jumping too high? So let's imagine there's 2 satellites on this elliptical orbit. There's 2 satellites on that elliptical orbit. And then there's a satellite in the middle. So the 2 satellites on the elliptical orbit, I should have drawn this. One is on the bottom end of that ellipsis, and one is on the top end of that ellipsis. And then a third one is in the middle of 2 ellipses. So that's kind of how it functions. It wasn't explained really well. So that's as far as I've gotten with my understanding. If somebody else has a better understanding, I'd love to hear it after the talk. So what this does is it reads the GPS signals or any of the other GNSS constellations and feeds it back to those specific regions. So for the QZSS, it's for the Asian Pacific region, and it's not a perfect ellipsis or elliptic. I'm probably not using the wrong, I'm using the wrong word. The infinity symbol, and it's kind of bulbous down at the bottom. So anyways, we're kind of going off into the far reaches, but I did want to make you aware of those systems. Then there's a whole different category, SBAS, satellite-based augmentation systems. And these are, I explained this a little bit better later because I made up my own slide. I wasn't happy with this slide. But this reference, but this was really cool too. I really liked his reference station here. It goes to the master uplink station, communicates with the SBAS satellite, and then it communicates with your rover, which is in this case the drone. So that's kind of how he portrayed it, and it's a little bit different than RTK, but we're not going to go over RTK today. So what satellite-based augmentation systems exist today? So when I first saw this reference, I was like, that's odd because I've only ever heard of, why do I have a picture in a picture? Okay, please ignore the picture on top of the picture, but I've only ever heard of WAAS, WAS, or EGNOS, but I had kind of heard of the one over Japan, the MSAS. So I was like, why hadn't I heard of this? So then I found this better graphic from Space Hubs Africa, which actually talks about which ones are operational already. So I don't know if you want to write these into your guide, but you can write down the ones that are operational because you will see these acronyms in your spec sheets. You'll see them detailed when people talk about GNSS. And you just want to just be aware that they're there. You won't get tested on it, but I just wanted to explain what they are. Okay, why don't they run into each other? Because they have different orbital altitudes. And I know it seems obvious once you know, but I was like, I just wanted to know how they were all coordinated. So in the middle Earth orbit, which is right here, this is a great graphic. It's from Wikipedia, and CM Glee made it, but it's used like hundreds, maybe thousands of times. It's really great. I'm only using the top half, so I could fit it onto the slide. But you just want to keep in mind that we're in the middle Earth orbit for the GNSS. The Hubble, of course, is in the lower Earth orbit. And I'm really excited because a ton of satellite systems are coming on in the lower Earth orbit and may replace our 5G. Where do SBAS fit in? So here's another representation of that same idea. So we have the low Earth orbit, we have the middle Earth orbit, and then we have the geo orbit, which is the farthest out, and where the SBAS satellite-based augmentation systems reside. So here's, I just thought I'd throw this in. This is from Wikipedia. It's not up to date by a far stretch of the imagination. There are many more systems here, but you may be interested in Globalstar because if you have an iPhone 14, you have the emergency services available now through Globalstar, and they went bankrupt, came back to life, somebody bought the assets, and now Apple is using those satellites for that system. So also Amazon is bringing on a new project. It's pronounced Kuiper, but it's spelled Kuiper. So but they're coming on board, and I'm excited about that project too because that is supposed to bridge the digital divide, particularly in America where people don't have broadband at home. It's supposed to make broadband available for all. So GNSS frequency guide. So this is on the back of that paper. So up until now, all of our tracking devices have been using L1, focused on the 1575.42 frequency. And we've mainly been using the civilian signals, also the coarse acquisition signal. So the C/A is actually coarse acquisition, and it's not coarse as in like traveling coarse, but like coarse as in grains of sand. Thank you. So if you need to spell that out, and I should have spelled that out here. And it's important to note that L1's the only signal that has the coarse acquisition available. It does have civilian signals, and other ones have civilian signals, but it's the only one with the coarse acquisition signal. Okay, so L2 is also here, and it's been around for a long time, but it's still being listed as incomplete. But you can still build a system using it. The newest one, it's been deployed in 2021. It was quietly deployed, but a lot of manufacturers have picked up on that. They've started making modules. You should find those modules out and about today. So if you want to make a device that is more accurate at tracking, I recommend combining L1 and L5 and looking for those modules. And I was like, well, but what about L3 and L4? So this is the explanation on that. So for nuclear reasons, L3 and L4, ionospheric correction, but we don't hear much about those signals these days. Okay, GNSS signal frequencies. I purposely made some places blank on your worksheet. Your job is to fill those in. Ready, go. Okay, you want to focus on the upper L band because that's the one that all modules use. So let's go ahead and fill in the easy ones, ARNS, RNSS. They don't get discussed a lot. That's why they're in the top, and we kind of breeze by them. But they're there, and they're down in the key below. So in the key below, please label GPS bands. They're in the yellow. And the GPS frequency band here is the L1. That's the number one, the one that's not used number one, even throughout the world. So just because GPS has been around since 1981, it's the frequency that the rest of the world uses still. GLONASS bands. So keep in mind that your G1 GLONASS band over here is not contained around the L1 band here. So when you pick out your external components, like your SAW filter and your LNA, you want to make sure if you're going to include GLONASS, that it includes those frequencies as well. Galileo bands. And those, because G was already taken, go by E. So the E1 band encompasses the L1 band. And then the BEDO bands are actually surrounding the L1 bands. And this is interesting because it's called the B1, and then I've seen most of the time it's called B1-2, but it can be called other things as well. And when you're talking about frequencies, you want to focus on the 1575.42. Anytime you're searching on DigiKey or whatever, that's the frequency that you want to target. So as I said before, 2021, this band got added, so 1176.45. And I noticed there's a mistake in this reference. And it's interesting because I love this chart and I've used it for a very long time. But I think they copied this mistake from, because I think it's based on the one that's actually on Navipedia. So please go ahead and write this in because this will be the next band that's coming alive soon. So it's the 1227.60 megahertz band. Okay, when you're finished writing, please raise your hand so I can get like a gauge of the room. Awesome, awesome, awesome. Okay, thank you. You can put your hands down. All right. Okay, are you ready for me to blow your minds?
Yes.
Okay, this is what it actually looks like. So this is all that you wrote down just now is on the upper L band side, this side right here. And these are actually more accurate signal representations. So let me give you a close-up of the one in the upper right-hand corner. So just to kind of break this down a little bit, these are the different signals that are actually within that band. So that's why it looks like that. This is just a cursory look at this format. Okay, you guys ready for GNSS 201? Yes! Okay, great. How to track your dragon, GNSS 201. Okay, first of all, think of your target device. You can even write it down if you want. Are you tracking your kid? Are you tracking your spouse? Are you tracking your, I don't know, runaway pet ferrets? You need to ask yourself a couple questions. Okay, everybody have that in mind, what you're gonna track? Okay. Does it need to be accurate? Say yes or no. Okay, does it need to be low powered? Say yes or no. Oh, nice, we got a no over there. Do you care if it's expensive? Okay, whoops. Fast and dense areas? Okay, and does it leverage like cellular, Wi-Fi, LoRa? It could. Okay, excellent. So these will be important later. So the accuracy, so like tracking stolen cars, you want to know where that is. If you're landing an airplane, you want that to be kind of accurate. If you're berthing an ocean vessel, like up to the dock, you want to know. So we're going to go over how differential GNSS works. This is called DGNSS sometimes. So basically, you use a ground station, and then it gives you the differential information. You compare your differential information with what your rover has received from its own satellite information, ephemeris data. And so you use those and use those calculations to be able to create a more accurate picture. So instead of 10 meters of accuracy, you're getting up to 10 centimeters of accuracy. It's quite good. Satellite-based augmentation system works kind of similarly, except instead of a ground reference station, you have a satellite-based reference system. Multi-GNSS, just to break down the vocabulary here. So this is when you have multiple systems. So you have Beidou, you have Galileo, you have GPS, and you're using all of that information to create a very accurate picture of where your rover is. That's the D-Track 400. Okay, the D-Track 5000 is using the GPS L1 and L5. So same satellites, you're just using different frequencies from those satellites. Okay, do you need speed? Does it need to be fast? So for 911 calls, you definitely want those to be, you want to know exactly where that person is to help them. So some things you can do to augment your GNSS signal is to use Wi-Fi, LoRa, or cellular, and use the computational power of that. And they can give you ephemeris data. This is great, especially if your rover is in between buildings or trees, or just in spaces where it's hard to get a signal to. Frequently, you can feed that signal to them so that they have the ephemeris and almanac data already calculated and already fixed. Because sometimes when you're in these crowded areas, it can take more than 12 minutes to get a signal, and your battery's going to die. So it's helpful to augment it. So timing, it's the song time. It's time for the song, because we all need a break, right? I need a break. You need a break? Okay. Okay, so here's how the song goes. So who's ever been to camp? Has anyone ever sung like a camp song? Yep. Okay, Joshua, I need you for this. Okay. Okay, do you mind coming up here with me? Okay, for those of you who may not know, I've been had the pleasure of working with Joshua Wise for the last year. Would you like to say anything about yourself?
No.
Okay. Okay. He will be singing along with, if you're singing along with him, you're singing the Galileo portion. Okay, but first I'm gonna warm up the crowd, okay? So we're gonna start on this side. And if you could just, when I stand in front of your row, if you could just copy what I'm doing, okay?
This is news to me, by the way.
Yeah, okay. You ready? Unsa. You know GNSS? Unsa. S-bass. Oh wait, that's not sexy enough. Hold on. S-bass. And
Galileo!
we have to do the full thing. You said, yeah.
The thing is that I don't know much Queen. That's kind of the only Queen that... Galileo Figaro, that's all I know. That's it.
Okay, thank you everybody. Thank you. Awesome. Okay. Oh wait, can you sing it? Get up here. Okay, thank you very much. I knew it would be the dry portion, so we need a little break. Okay, timing considerations, battery consumption. So you want to determine if you're checking in weekly, daily, hourly, every 15 minutes. If you're tracking a spouse, maybe every 30 seconds. So that's how my spouse checks me. So I always forget to tell him where I'm going. Okay, so standby mode, low power mode, backup mode. These are all really valuable when you're talking about checking in. You have a cold start, a warm start, and a hot start. So it has to deal with if you already have the almanac data already in your system. So those are different. And depending on the module that you have, they may have slightly different definitions of those particular statuses. So you want to work with those for your timing considerations. So we had one module that it took them over 12 minutes to get to the low power mode. So it wasn't very low power in the end. Okay, cost. For battery powered devices, I'm sorry, the battery powered devices is actually for the next slide. It's a misspelling, but cost considerations, some things to really keep in mind is that especially for boards with radio frequencies, you don't want to be short-sighted about spending money around that radio frequency trace. So those peripheral components, like the SAW filter, like a notch filter, like TVS diodes, all of those components, you'll be like, oh, I should just really take the one that's 1 penny less. But if you do an excellent job at designing your radio frequency signal, you can save dollars on the battery in the end. And then it also decreases the size of your overall tracking device as well. So don't scrimp on the component costs on the radio frequency trace for the GNSS in particular. So firmware development costs, so even if the module is $2 less, but requires, over $200,000 and 8 months in firmware development, you may want to pass. It depends how long your device is going to be out there. If you're just making a prototype right now, you may want the solution that's just the easiest to bring aboard quickly. PC fabrication cost, time and availability. So the HDI PCBs can take 3 days longer. But as of November, a lot of fabricators, PCB fabricators, were making it free. It used to be a really exorbitant cost to do like VN pads for small BGAs and things like that. But like, what was it? JLC PCB was the first one to just say, hey, it's free, everybody. So please take advantage of that. Those use less chemicals when you have an HDI board because it utilizes lasers instead of exposing a PCB to image. So don't think I explained that well, but we're moving on. Unknown module vendors. So in my search, we did consider some generic modules, but at the same time, you don't know if it's going to go out of stock. And also, your PCB fabricator can refuse the job. Sometimes they only wanted to work with, approved vendors. So that's something to think about. Supply chain, module A is $2 less than module B, but isn't easily available in large quantities. So these are all considerations to think about when you're thinking about cost. So this is the battery-powered devices part for power consumption. So really important thing to keep in mind, most specification and data sheets for the modules list their power consumption in milliamps, but what they don't point out is what voltage that's at. So you really need to make sure that you do the math, convert it to watts, and compare all of your selections based on wattage. So if you don't do that, you'll get bit really hard. So I gave some examples here, but and then you want to keep the time to first fix. That's what TTFF is. So if the module takes a long while, and I already gave kind of this example, we had one that took over 12 minutes time to first fix. And so you want to calculate how much of your battery will be consumed. I walked through the math here. And then component selection besides the GNSS module. So this is the meat of it all, everybody. This is the most heinous example. So this is if you're not using a module that may already have these elements in it, but you want to know about these elements so that even if you're picking out a module, you want to go, oh, does it already have the LNA included? Does it already have the SAW filter included? Those kinds of things. So this is an inductor capacitor filter, it's usually L-shaped, that we put on in the beginning. The SAW filter is the surface acoustic wave. I always want to make sure that I get that A right. The low noise amplifier is also, it boosts the signal once it's been filtered out. So you really want that in, because it's a really light signal, and you really want that boosted before you do all your calculations. The notch filter, so this can be used for many things. One interesting thing is if you have LTE on your device as well, and it's an IoT module, it's probably transmitting in the 700 megahertz frequency. Unfortunately, for that 700 megahertz frequency, the second, sorry, I'm blanking on the word for it now, but thank you, second harmonic, thank you very much. Alvaro, saved me again. So the second harmonic is actually at the 1575 megahertz frequency. It's really unfortunate. So you can sometimes notch it, like if you're really precise, you can kind of notch it out. That's something you could use the notch filter for. Another thing you can do is just not run the GNSS while you're running the LTE transmission or reception. So that's just a consideration to think about. So not a lot of people know about that, and I probably should have documented that a little bit more here. I will in the future. Matching Pi network, You typically have that for a radio frequency. It's a capacitor inductor kind of scenario. And the reason why it's called a pi is it's usually in a pi shape. So it has the capacitors going this way, and then you may have capacitors coming down or inductor depending on how you have your setup. And then the ESD TVS is really important if you have a UFL attached, like peel and stick antenna, and you're trying to test all these different peel and stick antennas. You want to make sure that, what's it called, the human body shock? There's a technical term for this, but you want to make sure that you don't fry your equipment. And so you want to make sure to put the ESD TVS diode on there as well. Sorry, that was a real rush through the overview though. Thanks for hanging with me. And then, yeah, decide which frequencies you will target, particularly your SAW filter. Okay, yeah, I already covered all that. One, just PS, by the way, I learned that in the code, so for example, the original code that I was working with, everything was listed in GPS, even though we were starting to use other constellations. And so because of that, I wanted to change everything to GNSS, and I kept misspelling it. So to get around that, I noticed that there was another vendor that just used PS for positioning system in all their firmware. I highly recommend adopting this habit. And you'll be able to adapt when the low Earth orbit satellite systems come in. So the GNSS modules that are available today, the well-known ones are on the left, the lesser-known ones are on the right. If anybody has dealt with the lesser-known ones or ones I haven't even heard of, please let me know. I'd love to learn more. Because you're all here today, I'll give you the tip. So Sony and Skyworks, I would highly recommend just checking those out. You may not be able to afford them. They may not talk to you, but those are, and this is, I think this is it. Yeah, this is it. Thank you very much for your attention today. I really appreciate it. Do we have time for questions? Okay.
So for questions, I can't run around with this wire tonight, so if you want to come up and line up over there, or actually over here, then happy to take questions. Or maybe better yet, I'll just, you can just repeat the question.
Okay, that's perfect. Let's do that. Okay, I'll be repeating the question. Any questions? That was a lot of information. I can imagine if you don't have questions right now, but I'm happy to take them if you have them.
I'm curious about the non-disclosure agreements that are typically, have you experienced that most of these vendors want to sign an NDA or?
That's a good question. So the question is, do most of the vendors want to sign an NDA? So typically, yes. But Nordics, a lot of Nordics information is online. So if you want to get started, I highly recommend using a Nordic module because just all the documentation is there and they're pretty easy to get. Yes?
You touched on low Earth orbit GNSS satellites. How quickly do you think those will mature and become in wide use? And what do you think will happen to the traditional MEO and GEO?
That's a really good question. So the question was, how fast will the evolution be to the lower Earth orbit satellites? And then will we lose kind of our usage of the middle Earth orbit satellites? I think that we will always have the middle Earth orbit GNSS because we've just had it so long. It'll probably be with us a ton longer. But as for the lower Earth orbit satellites, I think it'll take about 5 years to get those established. They're still kind of in the baby stage right now, but they are available, and the more systems we can build around them, I think the sooner we can all leap to that system. Yes?
So when your diagram that showed that the L
L1 and the L5 satellites, did they put them up in orbit with the ability for updates and frequency changes and things like that? So how did-
Yes,
how did that
yes.
work out?
And probably that may also be the reason why they're, the constellations are, I'm so sorry, I need to repeat the question. So the question was,
L1 and L5 came on later.
Right.
On the same satellite. How were the mechanics of getting that frequency in there?
right. So L1 and, so L5 came on later. Yes. So the question was, how did they update the signal? So for example, up to the L5 signal in later satellites. And the reason is that I talked about that there's a 24-unit constellation, but they always have like 3 extra satellites. So I believe that they take, one satellite offline so they can update it and put, substitute those 3 in, and then update the technology or the signals, test them, all of those kinds of things. But the shorter answer is that all of the last generation of satellites had those capabilities already built in. It's just making sure that they were all coordinated once they got up there was the big job. So, yes.
Yeah, just a comment on the, your well-taken point about the component selection and how key it is to spend a little more and not cut corners. Another one to consider is the clock source, that you need to have a temperature compensated crystal.
Oh, that's a really good point. So not a question, but a point, but you really need to have a good clock signal for your device that's being tracked. And what is your name?
Pete.
Pete brought up that it's good to have a temperature-controlled crystal for that. So, and I'm sorry, that's the last question that we'll have, but I'll be available outside after this. And thank you again for attending. I appreciate it. Thanks.
Thank you very much. We'll be around later today?
Yes,
Okay.
absolutely.
Sorry to cut questions off, but we're running into the next session. So everyone, please go to FMH second floor. Reminder that the door outside the room is locked all day today, so hopefully something will, we should have something down there that's going to help let you out. But be aware of that as you use the Thanks.
First of all, welcome and thank you all for showing up here. And since it's my first live talk post-pandemic, I'm going to get it. Everybody smile. If you don't want your picture on social media, turn around and always smile. Okay. I don't know if it'll be on social media. So anyway, thank you for being here. This talk is about taking the leap from microcontrollers to FPGAs. And does everybody know what an FPGA here is here? Okay, so I think most of us are familiar with them these days. They're out a lot more in the press, a lot more people are writing about them, talking about them. They're some pretty easy to use, easy to get started with products. There are products out there, two of them right here that I'm familiar with. The pictures of a tiny FPGA and one big square with their icebreaker. Great little barriers to entry. But what happened to me is I was a microcontroller expert. I spent years and years and years programming, C assembly mostly, and some other languages. And then I was convinced to take the leap to FPGAs, and I thought that's really cool. I started looking at the language. Syntax is very familiar. The arrangement of the files is very familiar. But there are some things that I discovered that coming from the microcontroller world actually caused problems. And so I made some terrible, terrible mistakes. And I was doing this publicly. I was writing a column about this as I learned FPGAs. So I would write about something, this great discovery I made about how these wonderful tools work, and I put up a code sample, and then down in the comments, all of these FPGA experts from around the world would go, Dwayne, let me tell you something. So, it was a fun process there, and, I don't mind making mistakes because really it's all about what you do after you make a mistake, how you recover from it. But there were a lot of frustrations there. And so that's what this talk is all about. You're used to programming, you're familiar with programming, and you want to start using an FPGA. So what are you going to trip over? Now, this is not a comprehensive course. You're going to have to learn about a lot of things in other places as well. But what this is going to do is outline some of the most significant traps that you'll run into. And so you remember this, or you can download this PowerPoint from my website. And as you go through this journey, hopefully this will be a little bridge over some of these little tiny chasms that you'll run across. So first of all, why in the world would you want to use an FPGA other than the fact that they're cool and they're different? Well, you're creating hardware in an FPGA. So you are designing and developing essentially a chip, a custom ASIC. But it's a custom ASIC that you can change every single time you power it on. And that's a marvelous thing if you use a lot of digital logic or you need to use a lot of digital logic. And then one of the other things that I find is really cool, excuse me, sir, could you raise your hand? Take it back down. Raise your hand. Take it back down. Raise your hand. Take it back down. So that's the software world. Everybody raise your hand simultaneously. Take it back down. So however many people, that's parallel processing. That's something you do with FPGAs, or you can do with FPGAs. And in this particular illustration here, I was working on a robot, and I had all of these little microcontroller boards that control motors or sensors or whatever. And I wanted to feed them into a main microcontroller. And then scan through all of them. Well, if it's a mobile robot, your speed is dependent upon how fast the motors can go, but also how fast you can see what's going on around you, do the sensor fusion, and then take your next move. If you've got to scan around all these sensors, that takes time. With an FPGA, I can create as many different I2C interfaces in that FPGA as I have pins for, and as I have fabric inside of the FPGA, and run them all parallel. Parallel processing easy. So what I found is, it is a mysterious world, but it's not as big a jump as I thought. There are now FPGA development boards that are $100 and less. And, you know, if you're in the corporate world, well, you don't have to worry about that so much, but if you're a hobbyist or in an unfunded startup, a maker, that's pretty important. So, Tiny FPGA, 1-bit squared, Papilio, there's quite a number of these things. You can just Google inexpensive FPGAs. And a lot of different options. So let's look at what's the same what's pretty much the same as a microcontroller and what's different. So they use an IDE. How many of you program in IDEs? How many primarily program with the command line? Okay, you can program these things with command line also. IDE is most common. You got multiple files in the development set, that's very familiar. You've got multiple language options, although not as many. You'll hear the term Verilog. That's the one that I use the most. It's one of the more popular languages for FPGAs. VHDL is another one that's one of the more popular ones. MyHDL is an open source based on Pascal. There's System Verilog. There are people who program them in C and a few other things. Primarily Verilog and VHDL, but there are more and more software tool sets opening up for these things. So you have some flexibility, not as much as microcontrollers though. You code and then you implement. And then the syntax is often pretty familiar, although that can be a problem, as I'll show you. Not the same. You don't turn it on and go. Most FPGAs, you've got a ROM, and you've got the FPGA, which is empty, sitting there brainless. You power it up, it loads the bit file, that's what we call it, once it's crunched down, bit file. Loads it into the FPGA, turns that into an ASIC, and then you're ready to go. And that can be pretty quick, or it can take, 20, 30, 90 seconds, maybe even longer. So you're instant on like you get with a microcontroller, don't expect that. The FPGA isn't running code, so you're not running your program. Unless, of course, you can actually create a CPU inside of the FPGA. Then you have your code that will be running on that CPU along with all of your custom hardware. You are literally creating an ASIC that is then a piece of hardware. And you have to wire up the chip pins to the innards. Some microcontrollers these days have crossbars where you can change where a peripheral sits. Every single pin, or almost every single pin on an FPGA is that way. You have to assign it before you can do anything with it. You've got your brains, you've got a crossbar all over the place, and you tell it where that signal is going to go. Okay, so what do you need to get started? Digital logic knowledge is really, really handy. Although you can learn digital logic as you're going. But most folks in the computer industry have some level of, you know what an AND gate is, or an AND function. That's really, really handy. You'll need to know that at some point, but you can learn it as you go. AND gates, flip-flops, common terminology within the digital hardware world. Familiarity with IDEs or comfort level with command line programming, either one. And then, as I said, microcontroller programming experience is helpful. It will both help and hurt. And probably programming microcontrollers is more relevant than if you're an applications programmer. So development environments, all of the major brands have them. There are some open source development tool chains coming out. It's a tool chain that's like you've used your entire careers. Okay, so you've got it, and now what do you do with it? And this is where, again, this is not a detailed tutorial. Remember that. These are the traps, but I'm going to walk you through the order that you go here. So the first thing you need to do is define what they call constraints. And that basically is things like, okay, pin number 1. What goes to pin number 1? Is it an input? Is it output? What voltage is it using? Things like clocks coming in, You define all of those things in what's called a user configuration file, user configuration file, logical preference file, lattice preference file, a couple of different names, but if you hear UCF, LPF, what you're doing is you're connecting pins to something inside and you're defining the operating parameters, voltages, timing, things of that sort. Then you code, you write code, that's pretty familiar. Then you simulate. In most cases with an FPGA, you want to simulate your design before you crunch it because it can take an awful long time to synthesize it, synthesize it into the code that's going to work in your FPGA. Hours, sometimes days to do this. So most of the good, well, all of the big commercial tool chains have a simulator. And that is exactly what it says. It's simulating your design, showing you the timing. You can give it inputs and outputs, and you see if it's going to work or not, and hopefully catch all of the major traps there, the major bugs there. Then you synthesize it, you crunch it to the final bit file, and then that is what gets loaded onto your FPGA into the non-volatile RAM, and then a power up goes from that non-volatile RAM into the FPGA. You've got the three primary file types, and again, this is not absolute, this is more abstract. There may be other types, but in general, you've got the UCF or LPF defining the pins, port locations, timing parameters. You've got your main code, and then you've got modules. And that's actually pretty familiar. You know, if a program, you might pick microcontrollers. I've got setting all the bits, the configuration bits. I've got my code, I've got my modules. Again, very familiar there. So here is a UCF file. And I'll go do this. So there's a lot of stuff in there that may or may not look familiar and probably is meaningless if you haven't used one of these things before. Yeah. In the blue, those are labels that I have created. They're not reserved words. It's like a variable name. There are rules for them, but basically I'm creating those names. The physical chip pins, BGA, so it's a big BGA that this one was referring to, so it's got A through at least V, and then down 20 pins or something down. So those are the pin numbers. I'm defining, so I've got a clock coming in. I've called it clock 66 megahertz because it's a 66 megahertz clock, very original. And net, that is essentially a wire. I'm connecting that wire to pin K15, and it is a 3.3 volt CMOS signal. So you can see all this information in there that would be defined in your microcontroller by the people who laid out the silicon. It's here in this. Now let's look at one individual line down here. So this is a button, reset button. I called it user reset, again, very original there. So it's on pin V4, 3.3 volts, and I've got a pull-down resistor. Your microcontrollers, typically you can add a pull-down or a pull-up resistor either in the configuration or on the board. You can do that here in the UCF file. So now on my board, so that's the board there. That pin is labeled SW4. There's a couple of different here, couple different pins or switches, and I could pick any of those to be my reset if I wanted. So now in step 2, the physical board, the PC board, you can see that's, well, you might be able to see, that goes from the switch to pin V4, and over here, pin V4, I'm calling it user reset. So now I have taken a random switch, I've connected it to the FPGA, and I've given it a name that I will now use inside of my code. So let's go ahead and, technical difficulties. So let's look at the Verilog code file, which is the main file. This is like your .c file, or for whatever language you're using.
So you break it up into a couple different parts here. The modules and modules and ports, you see up there, clock 66 megahertz, user reset, LED. Those are connected to these labels here, which again to the physical ports. So this is telling my Verilog code what it is that I'm going to be doing. So I'm calling those inputs wires, outputs wires. A wire is really a wire. Some people will refer them to nets wires, but we're telling them it's a wire. And I start it with the parentheses and end it with an end parenthesis and a semicolon. That's familiar syntax. Next, I've got some more wires here, and those are declarations. So those wires aren't going to the outside world. They are wires going from one part of my FPGA to another. Now you see this assign. Assign is something different. I'm going to talk about that a little bit later. But what that's doing is making sure a signal or a register or value is always available at the clock enable. So I'll go into that more detail there later. The BFGCE, that is calling an external module. So like in your C code, you call a library function. That's doing that, except here, you're not calling that function at runtime. What you're doing is you're telling the system that I want to build a clock. So over here is a template of a clock. I'm going to build that clock when I power this thing on and load the bit file into the FPGA. So that's what that's doing there. Register, I'm defining a place to put the LED counter. And 26 through 0, so I'm reserving 27 spots for that LED counter. It's not really an array. It is a set of bits, a register, and that's where I'm going to be storing that data. Now we've got clocked circuitry. So some things in an FPGA happen with each clock step. Do this, do this, do this, do this. Do this, do this, do this, do this. Other things are like an AND gate. You've got your little proto board, you put an AND gate down, you put two ones in there, and instantly there's a one on the outside. Well, instantly minus some propagation delay. That's called, I'm sorry. I lost my terminology here. That's combinatorial logic. Excuse me about that. Combinational logic. So an assign means whatever is in LED count, it's always going to be available on that wire up there. So that always happens. That happens instantly. The always is like a looping function. Feel free to ask questions, by the way, as we're going along here. So now let's put some of these things together. Kind of the three major things you're going to be dealing with: wires, assigns, and registers. And a wire, again, a wire is just, you can't really see them, but a wire is just a physical wire. And the reason this terminology is so important is because when you're going from the microcontroller world, you've got C equals B, A equals 23, A equals some function. You don't really think about these things. A register is your storage. You can have something going from a register to another register. You've got to wire it up. And you've got to have that wire going through the, to your output pin. You can read wires, but if a wire doesn't hook to a register, there's nothing there or it's unpredictable. One of the first traps that I ran into was I had some wires going directly into some of my code, and the results were just weird. Somebody says, "Did you register it?" And I'm thinking, what? Do I have to call Microsoft and register a DLL or something, call it a DMV? No, it simply means you have a register sitting there that you're going to put that data in. So the wire is for reading what's in a register. The wire isn't for processing. I was trying to process on a wire. And if you have a ribbon cable sitting someplace and you try and do processing on it, it doesn't work. Works about as well as an FPGA. So that's why wires and registers are really important. The assign is basically making a permanent connection. So I've got the wires and the registers, and I put values in the registers. When I power up the FPGA, assign is going to say, this wire here, a wire, that's my term, is equal to whatever value it sees in a register or a wire. So that's always there from the very moment. And you can receive something on a wire. Let's see, what do I have here? I better drink water. So my middle comment there, an assign cannot be used within an always block, because the assign means to wire something up at configuration time, where the always block is our triggered module. So you can't assign something in a triggered module, it just always has to be there. Another thing that tripped me up is this here is in my UCF. You notice we saw the net commands, or the net declaration, the LEDs. Again, I was treating that like an array when I first started, thinking, okay, well, you've got LED 0, LED 1, LED 2. It's like an array. It's not. Again, this particular case, when it's called a net or a wire, it's more like a ribbon cable. You're transmitting information. So,
What's the difference between a net and a wire?
net is just another term for wire. You use them in different places. So, like in that particular case, net means I've got several of them together, a ribbon cable, where wire you can use as an individual one. So output wire, that I'm calling LED, now what I had to do is I had to create a register. Again, the register is that's where you store the data. It's like a memory cell, kind of like a memory cell, not exactly, but that's where you're storing the data. The wire connects between it. If you look at the little tiny loop there, the always and end, that's like your main loop or a main loop in a C program. So I'm counting in there, but I've got my assign outside of that. So I'm doing the counting inside. The assign is outside of the loop. It's always reading what's inside that loop. And this is what I was getting at before, clocked versus combinational. So clocked, like a flip-flop, again, you're doing something clock-based. Combinatorial, combinational, it's like a digital logic chip. You put something on the input, it's there on the output, minus a little clock propagation delay. So here, again, out of all of this, this is the clocked circuitry. So when you've got clocked circuitry, so you can do it in two different ways. You can have more of these always blocks. And I'm going to tell you something dangerous about side 2 in a minute here. But with C, you pretty much have one main, and it calls everything else. In your Verilog file, in your hardware description language file, Verilog, VHD, or whatever, you can have more of those main loops. So here in this particular case, I'm flashing 3 different LEDs independently. They're all on the same clock, but I'm not doing this in sequence. That's all happening exactly at the same time, like the hand raising, even though these are different main loops. You can do that with one clock. You can do that with different clocks also. Again, there's some dangers with this, but if you have to have a 66 megahertz loop and then a 100 megahertz loop, you can do that inside of an FPGA, provided you have the clocks available in your FPGA. So you can do things differently like that. Again, danger when you're matching those, connecting those two things up, but you can do that. And that's something you can't do in a microcontroller. So combinatorial, so that was the clock logic. Assign is the key. So from my prior Verilog code, assign clock enable equals user reset. None of that other stuff has to run. None of that other, I don't have to have my clock running because it's outside of the always block. I don't have to do anything. The minute that bit file is crunched into my FPGA, that assign on the top and these two on the bottom are in place, and they will always be in place until I power the thing off. So you can get yourself into trouble that way too, because if you're depending on something to happen in sequence, because I've put it in an order there, it's not going to work that way because they always happen. So down on the bottom there, gate out Y equals gate in A and gate in B. That's a simple AND gate. And that's combinatorial logic in its most basic form. So here calls it out in a comparison to the microcontroller world. So your while there, that's the loop that's going on. I'm doing essentially the same thing, except anything outside of the while loop, while one, my port A.0 equals flash value, nothing happens. All the math is still going on, all the logic is still going on, but it's not connected to the outside world. In the FPGA world, in the red box is roughly equivalent to what's there in the red box. My assign is outside of that loop. And from an MCU world, you might think, oh, it doesn't happen. But it does, because that assign happens at power up, and when the bit file is loaded in. So that's really important to remember that some of these things, if you're used to the order mattering, if it's an assign, in general, the order does not matter. And this illustrates that again. So this is our hand raising at the very beginning. In the MCU world, you're calling a function, it finishes. You call another one, it finishes. You call another one, it finishes. These ones there, those three things are happening at exactly the same time. Right. So the full bit file is read in at power up, and then you have a piece of logic ready to go, and hopefully you have something in there to make it start whatever you're doing. Inputs coming in are being read, a clock is being...
Can I ask a clarification on that? I think earlier on you mentioned that can take a while compared to like comparing to
Yeah.
seconds,
Tens of seconds, sometimes longer for a really, really large FPGA. So registering, and I mentioned this a little bit earlier, but I wanted to give this a specific slide because this caused me a lot of trouble. I was trying to do processing on wires. I was trying to do math and have the result end up on a ribbon cable. And the experts were asking me, well, did you register that? Or a wire coming in. I was looking to do math on a wire when data might vary in the wire, and I'm assuming it's going to stay the same. So they were using the term registering. Again, it confused me. It simply means define a register and put the wire into that register, and then do your math, do your reading based on that register from a wire. And I wanted to call one thing out. It is noon right now, so if anybody's like getting really antsy, I won't be offended if you get up and run to eat or anything, but so we're running a little over time here. I hope that's okay. Mm-hmm. Yeah, that's a very good point. And some things, microcontrollers are not going to go away. CPUs and MCUs, TPUs are not going to go away. They have very important uses, and there are things you can do with them. Like if you need instant on, you've got to have a microcontroller. But say you're doing video processing and you need to process large chunks of data in parallel, that quadrant, that quadrant, that quadrant, or this layer, this layer, this layer. Each one of these always blocks potentially is processing a layer or a quadrant or a massive set of data. And you can get your big CPUs involved in that and burn up tons and tons of power, or you can do those things in parallel. So you can do things that involve massive amounts of data that need to be done in parallel. Yes, you could, almost anything you can do with an FPGA, you can do with a CPU or an MPU also. However, things like that are really well suited to this, or say you happen to be, your end product is on Mars. The Mars Perseverance rover has something like, I think it's 20 or more FPGAs in it. And if there's a problem in the hardware, you can send it new hardware, basically. So you can upgrade the hardware in place in a very remote area, and that's why one of the reasons why they chose to do that there. All of that parallel processing, all of the sensor fusion, with multiple cores, yes, you can do a pretty decent job of sensor fusion or with really high speeds, but there are times where you really need to look at things all at the same time. So if you're bringing in a bunch of sensors, you send that into combinatorial logic, and it's just there. You're welcome. So earlier on, I'll skip over this because we're running out of time because this is pretty important. But earlier on when I talked about you could do the same things on multiple different clocks, well, what happens sometimes, if you're not careful, is when you're doing things based on two different clocks, the clock edges don't line up. And so you try and trigger something before a transition from a 1 to a 0 is fully completed. So it's sort of like Schrodinger's logic. You don't know if it's really a 1 or a 0, or maybe it's both, or sometimes it's one or another. This is a really easy trap because the lure of multiple clocks is really enticing at times. Like I said, what if you want to do something on a 66 and a 100, or you've got something that's internally clocked and you've got something coming in that comes from a different clock, but it's asynchronous, so you have to determine the clock. It's really easy to enter a condition called metastability, which is when the FPGA, that particular logic gate, can't tell what's going on. It can't tell whether it's a 1 or a 0. And what you need to do is you have multiple flip-flops from one clock domain, so that gives it time to settle down. Again, metastability, remember that term when you're fiddling with these things. Spend a little time researching it because it's something that if you're not careful, it can really cause a lot of issues. Libraries and modules look very similar to the software world again. Very simple example, an AND gate. So I created a library function that was an AND gate, and then I called it multiple times. So you can see I've got inputs, 2 inputs, and an output, A, B, and Y, just like any other AND gate. Down in the bottom is the assign. That's actually the logic. That little ampersand is the AND function.
So with creating this, you're able to use a basic syntactic thing to bring it in?
Yes.
But if you're creating something more complicated, you'd have to build it up from syntactic blocks that exist?
Yeah, if you have multiple AND gates, you're going to have multiple layers of syntax, but you can have that particular symbol will be used throughout. And there are different symbols for different functions. Then there are also, there's some flip-flops that you can bring in. So it's a little bit different than the language you're using in C to do this, complex logic. But for combinatorial logic, that's the most simple form, and then you build it up from that. Okay, and this is what's really, one thing that's really, really important. Again, a function, you're reusing code. So I was the code when I was asking you to raise your hand, reusing me to say raise your hand, lower your hand, raise your hand, lower your hand. In an FPGA, you're not doing that. Each of these, we call it instantiate. You're creating a flip-flop in hardware. So that had called the same module, but it's a template. So when I power up that FPGA, I am creating the 3 different flip-flops. And they can be anywhere in the code that the synthesizer decides they need to be, or anywhere in the chip. So not calling, not reusing code. I'm creating logic from a template. Okay. So that was a lot to throw into half an hour. What I hope is you've heard some terms that will really, really help you when you start this journey. It hopefully will have dropped a little bit of the mystery, and that when you want to do this, you're going to go ahead and find yourself a little development board, a tiny FPGA maybe. I understand they were giving those out yesterday. Something like that, and just give it a shot. You can download this on my blog, download this presentation on my blog, and go through these different things and just trigger. Each of these are really research jump-off points. So each slide I've got here, there's some basic information to help you, and those are areas you want to study when you're taking your own FPGA journey. And you know, there's 1,000 times more than this. This is such a tiny little touch on the surface.
Can you recommend an IDE that's good for beginners? Because I've tried using Xilinx stuff, and that kind of suffers from the engineering problem where it's a really powerful tool that exposes everything all at once, so it's completely overwhelming.
I had a lot easier time with the Lattice tool set, and you know, we all have our preferences, but I found Lattice to be a lot easier than the Xilinx tool set. I mean, at some point, I couldn't even install the Xilinx tool set properly. It just was getting so complex and so in depth, and they're adding in all of their, you know, ARM programming functionality with this. So I'd take a look at something like the Tiny FPGA. It uses a Lattice, they call it the ICE chip, and I'd start there.
So you go from FPGA.
Their FPGAs tend to be more expensive, but some of them, like this ICE series from Lattice, are comparable to a mid-range MCU. You know, you can buy a development board for a few tens of dollars for one of these things. Crowd Supply has a couple of them, and they're showing up in other places as well. So for less than $100, you can get yourself a pretty powerful FPGA. For probably $30, you can get something that gives you a really good solid education, and you can use in your hobby or maker projects. You can use in in real world applications.
Earlier you asked the application programming to FPGA programming. Can you give a similar contrast between design and ASIC versus programming and FPGA?
That's going to be, I'm not going to be able to give you the most accurate information because I've never designed an ASIC. But I would say the big thing is, you know, looking back in my history to one-time programmable parts or, UV erasable proms. You design it and you program it, and well, there you go. So you have to have an awful lot more discipline, especially in the simulation phase with hardware, an awful lot more discipline, because with an FPGA, I mean, it can take a long time to crunch it, but then you can redo it. You don't have 100,000 units out in the field that you now have to recall. Mm-hmm. Mm-hmm. Yeah.
That's something that you can integrate into FPGA really easily.
Yeah.
You don't have to buy another chip to do that.
Yeah.
Maybe even have an SoC where you have a microcontroller and you have the same board.
Yeah. That's an excellent example. You can create a coprocessor of sorts. I mean, you can create a literal, central processing unit in an FPGA, or you can create a logic-based coprocessor. Specialized math, for example. You might have something that just does these complex vector analysis. CPU's off doing all of its stuff, running the device, and your FPGA is taking that complex, real specialized processing and handling that.
Maybe you can do simulation for synthesis for the performance. Is the synthesis deterministic enough that that's safe? You not having to, say, for design, interact with the synthesis where you want to simulate that?
Theoretically, the synthesis is close enough that you can synthesize and then run and have good confidence, but then you also have to test and verify. So you've got a verification. I mean, if it's not the real thing, it's not exact, but these days they're pretty darn close. Anything else? Well, thank you all so much. And go enjoy your lunch. Sorry you're late. Well, what'd you think? Well, thank you. When I go through this talk, though, it's like, wait a minute. There are some things now that I have out of order that I rewrite. I do that every time. Oh, yeah. And I generally keep it in mind the underlying hardware and the difference between combinatorial. Yeah. You're welcome. Thanks for showing up. Thank you. Well, thanks for showing up. And it's good to see you again. Yeah.
All right.
Thank you so much for your help.
Oh,
So often I come to these talks and it's like I just have to figure out what's going on here.
yeah.
Nice to have support right there.
Cool. Well, we're all just figuring it out too, but it comes together somehow.
Test.
Okay. Wow, that sounds plenty loud in the room.
Yeah, quite loud in the room.
So it sounded like this the whole time? Okay. So let's just adjust the receiver up a little bit. Oh yeah.
There we go.
You speaking to it?
Testing, testing, test, test, yeah, it's not hitting the max, but it does sound pretty loud, so.
Okay.
Talking and talking, it, yeah,
Several decibels higher on the HDMI.
yeah, that should be good.
If you want to do that on a test stream
Okay.
and see how the sound goes.
Cool, cool.
Do you know where 219 is? Is it that one?
I'm not sure, what's in 219 right now?
They just switched workshop from.
Oh, yeah, I think it's one or two over this one, maybe. You need help with bringing stuff over?
I don't think so, but
Good. Yeah, right, it's something about conference days, everyone always runs low on energy and,
Yeah.
you know.
I think I will make a second pass at the body steel, I'll tell you that.
Good, good.
The,
Little boost, right?
Can I mess with the HDMI and get myself set up over there and just check everything out?
Yes. Cool. Yeah, like super self-explanatory.
Hey, Tim. Coming back later. Okay, so what I've learned is that my primary USB cable is dead, but I can back up.
Oh, good. Yeah, dead cables are the thing we've had all week.
The power cable for my laptop in particular is the dead one, so luckily I have a spare.
Good.
Otherwise, I would suspect that there are many people around here who have USB-C chargers, so
Right.
USB-C, HDMI. Okay.
Okay, so let's do a test of your setup. Should be pretty smooth.
I'm just gonna leave everything set up here once I, oh, hey, hey, nice. Lovely machine.
Right?
Power. There.
Oh, here. In fact, right in front of you, you can unplug the MacBook one. There, it's a very, very awkward place to just put one single outlet.
Great.
Not sure the thinking on that one, but
Thinking might be an overstatement for the design of that.
yeah.
Imply something that may not be true.
Right.
Yeah, here's one USB cable, there's no USB cable.
Cool.
There it is. So the question that I have is the terminal visible up there? Is
Okay. So, yeah. Now, were you hoping to use the down cam for anything, or?
I mean, the Good over here, yes.